morning, students. Now we go for the height balanced trees. See, trees with a worst case height of big O of log n is are called height balanced trees. These are the AVL tree, red black tree, and B trees. See here, AVL tree and red black trees are useful for internal memory applications, where B tree is useful for external memory applications. See, AVL and red blacks are the internal memory applications, and B tree are the external memory applications. So first we go for AVL tree. So what is meant by AVL tree? So AVL tree is a binary search tree in which the differences of heights of left and right subtrees of any node is less than or equal to 1. The technique of balancing the height of binary trees was developed by Edelson, Welsky, and Landis, and hence the given is short form as AVL tree or balanced binary tree. In 1962, Edelson, Welsky, and Landis are developed by AVL tree. See, an empty binary tree, capital T, is an AVL tree if T is non-empty binary tree with TL and TR as its left subtree and right subtrees, then T is an AVL tree. Here see, TL and TR also AVL trees. HL minus HR is less than or equal to 1. That is the height of left subtree and height of right subtree respectively. In an AVL tree, every node is associated with a value called balance factor, and it is denoted for the node X. See how to calculate balance factor, that is the balance factor of X equal to height of left subtree minus height of right subtree. So from the definition of AVL tree, the allowable balance factors are 0, 1 and minus 1. See for example, these are 3 levels. So 20 is the first level, 15, 40 second level, 90, 77, 16, 3 levels, and 90, 77, 16 are called leaf nodes. That is, there is no child. So always that is 0 is the balance factor. And go for the 15, the left child is 90 and the right child is 77. That is 1 minus 1 equal to 0. So 15 balance factor is 0. And go for right subtree of 40, then left is no node and right is 1 node, that is 0 minus 1, that equal to 40 is balance factor is minus 1. And go for 20, height is 2 minus 2, that is 15, 90, 77, 40, 60, 2 minus 2, that equal to 0. So only balance factors are here 0, minus 1. Okay. For example, see, if the AVL tree satisfies the properties of binary search tree, then it is referred to as an AVL search tree. Operations on AVL search tree. Insertion operation. Inserting an element into an AVL search tree follows the same procedure as the insertion of an element into a binary search tree. Already we have discussed how to insert elements in binary search tree, but the insertion may lead to a situation where the balance factors of any of the nodes may be other than minus 1, 0, 1, and the tree is unbalanced. So allowable balance factors are 0, 1, minus 1. Other than 0, 1, minus 1, that is called as unbalanced tree. If the insertion makes an AVL search tree unbalanced, the height of subtree must be adjusted by the operations called rotations. So if it is like the given tree is unbalanced, we go for the rotations. For this, consider n is the newly inserted node and capital A is the nearest ancestor which has balance factor of 2 or minus 2. Then the imbalance rotations are classified into 4 types. There are LL, that is left rotation, right rotation, left rotation, left rotation. See, LL rotation, new node n is left subtree of A RR is new node, N is right subtree of A, LR is right subtree of left subtree of A, RL is left subtree of right subtree of A. Here the transformations done to LL and RR imbalances are often called single rotations. Those done for LR and RL imbalances are called double rotations. So LL R are called single rotations, LR and RL is are called double rotation. See, first go for LL. In LL rotation, every node moves one position from current position. See, A, B, N. So B is the root node, N is the left child of B, A is the right child of B. Now go for RR. Every node moves one position from the current position. See, A, B is the right position, B is the right child, N is the right child of B. See, B is the root node, A is the left child of B, N is the right child of B. An LR rotation is a sequence of single left rotation followed by a single right rotation. In LR rotation, at first every node moves one position to the left and one position to the right from the current position. C, A, left, B, right, N. You can assign like that. Then here N is the root node, B is the left of N, A is the right of N. Then RL rotation is a sequence of single rotation followed by a single left rotation. In RL rotation, at first every node moves one position to right and one position to left from the current position. See, A, B is the right, N is the left, that is RL. Here N is the root node, A is the left child and B is the right child. Likewise, we can arrange the orders, then we can balance it when it will be unbalanced. Okay. See, for example, the given elements are 55, 66, 77, 15, 11, 33, 22. So now we insert an element 55. It is a root node. Here that is called, it is also a leaf node. So it is 0. The balance factor is 0. Now we insert 66. 66 is greater than 55. So we go for right side of 55. So see, in 66 is leaf node. So always balance factor is 0. Then go for 55. There is no left child, that is 0 minus right child is 66. One node is there. So 0 minus 1, that equal to minus 1 is the balance factor of 55. So now to insert an element 77, 77 is greater than 55. So we go for right. So right, already one child is there, that is 66. So 77 is greater than 66. Then we go for the right side. See, 77 is leaf node. So balance factor is 0 and 66. There is no left child. So that is 0 minus 1 right child is. So 0 minus 1, that equal to balance factor is minus 1. Then go for 55. There is no left child. But here two childs. That is the two levels. 66, 77. That is 0 minus 2. That equal to 55 is the balance factor is minus 2. See, always it will be done in right side. So we can go for RR notation. Why we go for RR notation? It is unbalanced. So only it is the balance factors are 0, 1, minus 1. Other than it is called as balance factor. In that process we go for the different type of rotations. Here we go for the RR, that is right notation. See, right notation, 55 is cosine A, 66 B, 77 N. Here N is the root node, that is 77 is the root node, B is the 66 and A is the 55. See, N, left child is B. Here B is the root node, left is A, right is N. See, B is the root node, left is A, right is N, that is 66, 55, 77. So 55, 77 are the leaf nodes, the balance factor is 0 and 66, 1 left child and right child, that is 1 minus 1, that equal to 0. So it will be balanced. So now we go for to insert an element 15. So 15 is less than 65. so 66, so we go for left child. Already one node is there, that is 55, then 15 is also less than 55, then go for left. So now we go for balance factors. 15 and 77 are leaf nodes, that is 0 0, then 55 is a balance factor is 1, that is 1 left, then there is no right, so 1 minus 0 1, then go for 66, left child is 2 and right is 1, that is 2 minus 1, that equal to 1, so it is also balanced. Now we go for insert 11. 11 is greater than, sorry, less than 66, we go for left, then second child, second node 55, go for left, then 15, go for left, then 11. So see, the balance factor is 11, 77 is 0, 15 is 1, 55 is 2, 66 also 2, but 2, when the 2 is comes, it is called unbalanced, so we go for rotation. So always it will be done left, so we go for the left notation, C A B N. So B is the root node, that is 15, N is the left child of 15, A is the right child of 15. So we check for the balance factor 0 0 0 0 1. So now it is balanced. Now we insert 33. 33 is greater than 66. So we, sorry, less than 66, we go for left. Then here the other node is 15. 33 is greater than 15. So next we go for right. Right is 55. So 33 is less than 55. Then we go for left. So now we check balance factors. 33, 11, 77 is leaf nodes. So there is no child. So 0. Then go for 55. Left is 1. Right is, there is no child. That is equal to 1. Then 15. Left 1. Right 2. So 1 minus 2. That is equal to minus 1. Then go for 66. Left 3 and right 1, that equal to 3 minus 1, that equal to 2. But whenever comes to, it is called as unbalanced. Okay, see, now check. It is unbalanced. Now we can apply left right notation. Okay, so A assign 66, 15 is B assigned, 55 is N, 33 is BL. Then there is no right child. Okay, so now N is the root node, B is the left, and A is the right, that is 55. The left child is 15, right child is 16, 66, and right child is 77. And 15 as the left is 11 and the right is 33. So now we check the balance factors. 11, 33, 77 is leaf, so 0, and 15, 1 minus 1, 0, and 66, 0 minus 1, and 55, 2 minus 2, 0. Now we insert 22. Okay. Now we go for deletion of element. So deletion AVL tree, deleting a node from an AVL tree is similar to that in a binary search tree. Deletion may disturb the balance factor of an AVL tree, and therefore the tree needs to rebalance in order to maintain the AVLness. For this purpose we go for the rotations. See, deletion of an element from AVL search tree follows the same procedure as the deletion of binary search tree operations. For how to delete in binary search tree already we have discussed. Likewise we have to go for here like, and but here when how to delete an element, we search for the rotation like balance factors. Okay, due to deletion of the node, some or all of the nodes of balance factors on the path might be changed and tree becomes unbalanced. To make it balanced format, it also requires rotations. Okay, in this case the deleting node is not available after performing the deletion operations. Hence, based on the balance factor of siblings of the deleted node, rotations are classified into 6 types, that is L0, L1, L minus 1, and R0, R1, R minus 1 rotation. So what is meant by RG rotation? Assume a node is deleted from the right subtree of a specific position C. After deletion operation, the sibling node B has a balance factor as 0, and then R0 rotation is used to rebalance tree as here. See, C, B and BL, B are left and right, C are right. Okay. When the balance factor B is 0, then we go for the B is the root node and the left is the BL and right is C and right B, left is BR and right is C1R. Okay. R1 rotation, assume a node is deleted from the right subtree of a specific position C. After deletion operation, the sibling node B has a balance factor as 1 and then R1 rotation use it to rebalance the tree as likewise. And R minus 1 is, assume a node is deleted from the right subtree of a specific position C. After deletion operation, the sibling node B has a balance factor as -1 and then R minus 1 rotation is used to rebalance the trees. Then L0, assume a node is deleted from the left subtree of specific position B. After deletion operation, the sibling node C has a balance factor as 0 and then L0 rotation is used to rebalance the tree. And L1, a node is deleted from the left subtree of specific position B. After deletion operation, the sibling node D has a balance factor as 1 and then L1 rotation is used to rebalance the trees. Likewise, L minus 1, a node is deleted from the left subtree of a specific position B. After deletion operation, the sibling node C has a balance factor as -1 and then L minus 1 rotation is used to rebalance the tree. So likewise, okay, same in binary search tree how we can delete. Likewise here also we simply delete the node. When we have to delete the nodes, it will be unbalanced. In that process we go for the R0, R1, R minus 1, L0, L1, L minus 1. Okay. Now we go for the B tree and also called M-way search tree. A M-way search tree, capital T, may be an empty tree. If T is non-empty, then it satisfies the properties as every node can have a maximum of M subtrees. A node with K subtrees will have K minus 1 elements where K less than M. All the elements of a node will be in ascending order, that is, if it consists element as K1, K2 and so on Kn such that K1 less than, K2 less than and so on less than Kn. Assume its children nodes as C1, C2 and so on Cn. The elements in C1 are less than K1 and elements in C2 are greater than K1. All subtrees are M-way search tree. Here 3-way search tree for example. So what is the definition of B tree? A B tree of order M is an M-way search tree and it may be empty. If it is non-empty, then the following properties are satisfied in terms of extended trees. So already we discussed what is meant by extended tree. So first one, the root node should have a minimum of 2 children and a maximum of M children. All the internal nodes except the root node should have a minimum of M by 2 and non-empty children and a maximum of M non-empty children. All the external nodes at same level. For example, we take for the order 3. Thank you.